Today we're going to talk about two new concepts, impulse and momentum. In class so far we've dealt with things that change, the velocity, the position, and in physics sometimes it can be advantageous to look at things that stay the same. And when something stays the same in physics, we say that it's conserved. So up to date, what we've been doing lately is taking Newton's second law, F equals to ma, and looking at the forces, drawing a free body diagram, and finding the acceleration from this. Once we have the acceleration, if it is constant, we can go through using our kinematics equations and solve for just about whatever we want to solve for. This, however, becomes very complicated if the force is not constant, and we've pretty much been dealing with constant forces, but sometimes the force isn't constant. And so the next couple of chapters deal with situations that can be helpful when the force is actually changing. And the first we're going to look at is impulse and momentum. So many forces are not constant. For example, a collision. In a collision between two objects, the force is generally not constant. And so right now we're going to look at two different concepts, impulse and then the conservation of linear momentum. Linear momentum is defined as with the letter P, so apologize for that. We're running out of letters here to use for our quantities. So P is equal to the mass times velocity. So a moving object has a linear momentum. This is a vector quantity in the same direction as the velocity. The units are mass times velocity, so units would be kilogram meters per second. And what we'll do a lot of times is we'll break this up to look at the vector components of this. All right, the x, the y, possibly the z direction if necessary. One thing just to keep aware of is that momentum can be negative. This will be something that can trip you up sometimes, so be careful. If we start with Newton's second law, we can get some insight into where momentum comes from. And so here I've taken Newton's second law in the x direction. And so I take that and replace the acceleration with the first derivative of the velocity, and then I do some algebra. All I've done here is I've taken the dt over to this side of the equation and then flipped the sides. All right. Now we have these two differential elements here, dvx and dt, which allows us to integrate both sides. And so we're going to integrate over the velocity in the x direction from the initial to the final velocity, and then for time on the other side from the initial to the final time. Now this integral here is actually not too bad. All right, so if I write this out, there's nothing in the integral here. It's a constant integral, and so the antiderivative will just be the x velocity evaluated from the initial to the final. And so we get Vx final minus Vx initial. And when I plug that into there times by the mass, you see that here I get the difference in the momentums. And so this is where we get our definition of the momentum from, just from Newton's second law. And then this side over here, we're going to name this side of the equation the impulse. And we'll talk about this in a second. So the impulse is best described by looking at a graph of the force versus time. And so here I have the force versus time graph for a non-constant force. This would be an example of a collision force. And so you see that the force starts out at 0, goes to some max value, and comes back down to 0. It's constantly changing. It's not staying the same. And we define the impulse as that right side of the equation from the previous slide. Another tricky thing here, impulse is actually letter J. Again, sorry about this. In physics, we got to the point now where we're running out of letters. But it's defined as this integral. Now, how do we think of integrals in our class in 131? Well, we'd like to think about it here as being the area under the curve. And so the impulse is going to be the area under the curve of a force versus time graph. This will be the way that you'll actually be solving if you ever have to solve for the actual integral version of this. A simpler way, which the book will use sometimes and will use, is to think about the average force. So the force is not constant, but we can come up with some sort of an average force that represents this impulse, and then set it up like this here, so that the impulse is equal to this average force times the change in time. A lot of times we won't care what the actual force is, and the average force would be good enough. And we look at the units of this, the units will be force times time. Both versions of this have the same units, and that works out to be kilogram meters per second, the same units as we get for momentum. Now if we think about this a little bit, When an object is acted upon by a force, we expect an acceleration. That's what Newton's second law tells us, F equals ma. This acceleration results in a change in velocity. But we expect the same with a non-constant force, and so after an impulse x, the velocity of the object should change. And so if we look at our new equation, which we'll write this way here, let's do it in the x direction maybe. And then we'll write our, over here just as the impulse. So when an impulse acts, and remember the impulse is essentially a force. If there's no force, the impulse is zero. So when an impulse acts, what does that do? Well, it changes the velocity. The velocity will have to change. And so this is just a rewriting of Newton's second law. There's really nothing new here, it's just a new way, sort of a new vantage point to look at it. And so we call this new equation the impulse momentum theorem. And in real compact form, it looks like this here. So the impulse equals the change in the momentum. Again, this is a vector direction. So here I've shown the x version. You have a y version and a z direction, a z version, whatever. So we write this out. The jx equals, here is the momentum actually written out explicitly. Again, you can also write this as the way we've been kind of writing it up to now, is something along these lines. All right. And another thing that the book will do, which is kind of handy, is it'll write it this way here. This is just the same equation, all right? And here it gives you a little bit a better conceptual way to visualize this. And so it says the momentum after, the final momentum after some interaction, like a collision or explosion, equals the momentum before, pix, plus whatever the impulse that arises from this interaction. Okay, it's a nice way to visualize it. So let's look at an example. Here we have an example where there's a baseball coming in at 48 meters per second and it hits a bat, okay? And the bat hits it, it's in contact for a certain time. If the ball leaves headed right for the pitcher with a speed of 38 meters per second, what impulse did the bat impart to the ball? Give this a try, pause the video, and then we'll talk about this in a second. Okay, hopefully you got that it was C. If you didn't, I probably got to guess where you went off. So the important thing here, as usual, is drawing a picture. So I'm going to draw a picture. I'm going to call the positive direction to the right. So here's the bat. So initially, the velocity of the ball, it's coming in towards the bat in my picture, and I get a negative 48 meters per second. Now the final case, so this is, over here is the initial case, this is the final case. In the final case, the bat goes off, it's got a speed of positive 38. Now no matter how you drew this picture, all right, you had to have it so that the signs of those two speeds are different, and that's sort of the key. So we use our new impulse momentum theorem. Here we're actually solving for the impulse, that J, and so here I plugged all my numbers in, the mass and the velocity, and the key here is that it's a negative 48, so that these two positive signs cancel out, and you actually add together these two terms to get the 12.04. And hopefully this makes sense, okay? The bat over here has to stop this speed and then give the ball this speed, and so it's these two reductions in the speed will have to add up, and this is what they do here. Now the problem could have asked next, what is the average force? And that's not so bad. The average force, remember, we can think about the impulse as average force times change in time. We know what the impulse is, it's the 12.04. We divide by the time and you get kind of a big force. So it's actually a big force, and of course these numbers are pretty typical numbers, and so this is a good estimate for the average force for a baseball hitting a bat. Here's another example. This one's a little more conceptual. A 2-kilogram object moving to the right with a speed of 1/2 meters per second experiences the force shown. What are the object's speed and direction after the force ends? So we'll pause the video, give this a try, and we'll talk about it. Okay, so I got the answer D, 1 meter per second to the right. And so let's look at this. So again, we're using our impulse momentum theorem, and the key here is now the impulse is going to be the area under the curve. And so I rearranged the equation this way here since we're looking for the final information, and so Jx is going to be this area under the curve in this particular case here. And so what is that for us? Well, it's got a height of 2 newtons. So here's my height of 2 newtons, and then the width down here of 1/2 second. And so altogether it's 1 newtons per second. And so when I plug that into the equation, I plug in the 1 newtons per second, and here's the mass of the object and its original velocity. So here I'm going to call this positive, so that positive velocity means to the right, which implies that negative velocity would be to the left. So we can be careful about what we get when we get our final answer. So when I add that up, I get 2 newtons per second, and then just realize that the momentum final in the x direction is just the mass times the velocity final in the x direction. So if I set that up, I can get that the velocity is 1 meter per second, which is positive, which means it's going to the right. All right, so just a little bit of kind of filling in some of the information here. Newton's second law can be written this way up here. All right, and that's how we've been sort of looking at it today. All right, and here we're saying this is how Newton originally wrote this. Okay, he said that the net force equals the change in momentum divided by the change in time, the derivative of the first derivative of the momentum over time. Now, if you take our definition of momentum and plug it in here, and then just make the assumption that the mass is constant, okay, it pops out, and you can replace this with F equals ma, which is the more standard that we have dealt with more often. All right, but these two are actually equivalent as long as the mass is not allowed to change. Right over here, if I pull the mass out of the derivative, I'm assuming that the mass can't change. And so far, everything we've dealt with in class, the mass has been essentially constant. And so in these situations, these two versions of the equation are exactly the same. So this new one, which actually was the way Newton first thought of this, all right, are equivalent. And finally, one thing that's going to be really profound, and we're going to deal with this a lot next time, is the idea of conservation of momentum. Now, how does this work? Well, we take this new version of Newton's second law, the net force equals the derivative of momentum with respect to time. Now, what happens when the net force is 0? Well, we get dp dt equals to 0. What does that mean? Well, if the first derivative of something is 0, that means it has to be constant. And so momentum versus time will just be a graph like this over here. All right, which means momentum does not change. It's not allowed to change with respect to time. Another way to think about that is think about our derivative. We can do this sometimes, is think about it as being a bunch of deltas. So delta p over delta t. Well, if that equals to 0, what I can do then, that means that dp equals to 0, because I can just multiply both sides by delta t, right? And then here it gets 0, and here it cancels out. And so if delta p equals to 0, our definition of delta p is p final minus p initial. That equals 0. That implies that the momentums are constant, are equal to each other. Momentum does not change, and so this is called momentum is conserved. So whenever the net force acting on something is 0, momentum will be conserved, and we'll use this much more next time.